Stokes Theorem. Stokes' theorem states, let S be an oriented piecewise smooth surface that is bounded by a simple, closed, piecewise smooth boundary curve C with positive orientation. Let F be a vector field whose components have continuous partial derivatives on an open region in R3 that contains the surface S. In this case, the integral along the curve C of the vector field dot product with dr is the same as the double integral over the surface of the curl of f dot product with ds, which of course is equal to the double integral over the surface of the curl of f dot product with the normal vector to the surface times ds. Okay, so there's kind of a lot going on there. So let's suppose we have a surface in R3 here, and then C is the boundary of that surface. And C has positive orientation, which means as we walk along the surface in a counterclockwise direction, the surface is to our left as we walk around this. And so what Stokes' theorem is saying is that the integral along the boundary is the same as the double integral along the surface. And so it's not that we use one of these over the other. Sometimes the line integral is easier to compute, and sometimes the double integral on the surface is easier to compute. And let's also not forget that when you're integrating on the surface, we have a couple of different choices for how we wish to do this. Right? We might use some kind of a parameterization, or we might have a surface defined as a function of x and y. Let's take a look at an example. So here we want to evaluate the integral along the curve C of f dot dr, where f is this vector field, and C is the curve of intersection of the plane y plus z is equal to 2, and the cylinder x squared plus y squared is equal to 1. And then orient C to be counterclockwise when viewed from above. Okay, so you can see our surface here, and then C is the boundary of that surface. So first, let's evaluate the integral along the curve. In other words, let's not use Stokes' theorem. Let's simply evaluate this. So our function f is the function negative y squared x z squared. And then we need our parameterization r. So if you imagine being on this curve here, we know that x and y have to satisfy being on the unit circle down below. And so therefore we can use the parameterization r is equal to cosine theta sine theta, and then z, but if we're on this surface up here, right, we know that z is equal to 2 minus y, and that's going to be 2 minus the sine of theta. And theta is between 0 and 2 pi. So now dr is simply negative sine of theta, cosine of theta, and negative cosine of theta. And now we're going to do f dot product with dr, but f now is going to have these functions substituted. So negative y squared becomes negative sine squared theta. X is cosine of theta. And z squared is 2 minus sine of theta, quantity squared. So now f dot product with dr is going to be negative sine squared of theta times negative sine of theta, which is sine cubed of theta, and this is not a vector. There we go. And then we have cosine of theta times cosine of theta, which is cosine squared theta. And finally, negative cosine of theta multiplied by this here is going to be negative cosine of theta times 2 minus sine of theta squared. So that is our function. So the integral now is going to be the integral of that. So that's squared. There we go. And then d theta and parentheses there. And then theta, of course, goes between 0 and 2 pi. So now we just need to evaluate this integral. So we're going to need a u substitution here. We need a half angle identity here. And then a second u substitution here. We'll just let u equal 2 sine of theta. So let's go ahead and perform all those off camera, and we'll come back right now. Okay, so there is the antiderivative. Now we just need to plug in 2 pi and 0 and subtract. And so, of course, when we plug in 2 pi here, cosine of 2 pi is 1. 1 cubed is 1. So we have 1/3 minus cosine of 2 pi is 1. And then we have plus 1/2 times, when you plug in 2 pi in for theta, you get 2 pi. Plus 1/2 sine of 2 times 2 pi is 0. Plus, and then we have 2 cubed over 3, right? Because sine of 2 pi is 0. 2 minus 0 is 2 cubed over 3. Okay? Minus, now we're going to plug in 0. We're going to get 1/3 minus 1 plus 1/2 times 0 plus 0 plus 2 cubed over 3. Now we just need to do some subtraction here. 1/3 minus 1/3, negative 1 minus minus 1, 8/3 minus 8/3. And so it looks like the only thing left over there is pi. So this is one way to compute the integral, which means directly. Now let's use Stokes Theorem. So Stokes Theorem says we can compute this line integral instead by doing a double integral along the surface of the curl of f dot product with a normal vector to the surface. So first, let's go ahead and compute the curl of f. So recall the curl of f is del cross f. So let's go ahead and do that, and we'll use a determinant for this. So here is that determinant, and now let's go ahead and go through and do the computation. So if we ignore here, we have the derivative with respect to y of z squared, which is 0, derivative with respect to z of x, which is 0. So the first component of our curl here is going to be 0. Now if we ignore here in the middle, we're going to have minus the derivative with respect to x of z squared, which is 0, derivative with respect to z of y squared, which is 0. And then ignoring the row and column here, we have the derivative with respect to x of x, which is 1. And then minus the derivative with respect to y of negative y squared, which is going to be 1 minus minus 2y, which is 1 plus 2y. So that is our curl. Now for the normal vector, remember we have a couple of options for that. So our normal vector is going to be negative partial derivative of g with respect to x, negative partial derivative of g with respect to y, comma 1. Or if you do it implicitly, it will simply be partial g, partial x, partial g, partial y, partial g, partial z. So it all depends on how our surface was given. But our surface was given as y plus z is equal to 2. So we can think of that as z equals 2 minus y. Okay? So our g of xy, which is our surface, is simply 2 minus y. So I'm not going to use this one. I'll just go ahead and use this formula here. And so the partial derivative of g with respect to x is 0. The partial derivative of g with respect to y is -1, so we have -1, which is 1, and then 1 again. Now, just to be clear, if I left it in its original form, y plus z is equal to 2, right? Or I could have said y plus z minus 2 is equal to 0. This could have been our function, and then you could have taken the partials and plugged it into here, and you would have gotten the same thing. Okay, so our normal vector is 0, 1, 1. So now we need to do the curl dot product with that normal. So that's going to be 0, 0, 1 plus 2y, dot product with 0, 1, 1. And this, of course, is just 1 plus 2y. And so now Stokes' theorem says we just need to take the double integral of 1 plus 2y dA along the domain D, right? And the domain D now lives in the xy axis, and that is simply going to be the unit circle down here. Well, because our domain is the unit circle, it would behoove us to use polar coordinates here. So in polar coordinates, of course, we know x is equal to r cosine theta, y is equal to r sine theta. And so this double integral in polar coordinates becomes the integral. Theta is going to go from 0 to 2 pi. R is going to go from 0 to 1. And we have 1 plus 2 times y, which is r sine of theta, and then r dr d theta. And now we're going to go ahead and integrate with respect to r. So don't forget you have to multiply r here. So that's going to be r integral is 1/2 r squared. Multiply here, we're going to have 2r squared. So the integral there is going to be 2r cubed over 3 times the sine of theta. This goes from 0 to 1, and then d theta. And then we keep on going here. When we plug in 1 for r, we're going to have 1/2 plus 2/3 sine of theta, d theta. And now we integrate from 0 to 2 pi. This is going to be 1/2 theta plus 2/3 times the integral of sine, which is negative cosine. And then from 0 to 2 pi. And this is going to be 1/2 times 2 pi minus 2/3 minus 0 minus 2/3. And that is 1/2 of 2 pi, which is pi, which is the same answer. Now, you tell me which method is easier, but we got the same answer using both methods. In the next example, we want to use Stokes' theorem to compute the double integral over s of the curl of f dot ds, where f is given as follows, and s is the part of the sphere x squared plus y squared plus z squared equals 4 that lies inside the cylinder x squared plus y squared is equal to 1 and above the xy plane. So what we have is a sphere of radius 2 and then a cylinder of radius 1, and we're looking at this portion of the sphere up here. Okay, so in this case, taking the double integral over s of the curl of f dot ds is likely going to be pretty involved, pretty difficult. So instead, we'll say this is equal to the integral of f dot product dr over the curve, the boundary curve, which is this curve right here. That will likely be much easier. So first, I just need to parameterize the boundary curve, right? The boundary of the surface up here, this boundary curve. And we know that if x squared plus y squared is equal to 1, right, then we can plug 1 in for x squared plus y squared here, because we're trying to find the intersection of those two surfaces. And we're going to have 1 plus z squared is equal to 4. That means z squared is equal to 3, or z is equal to the square root of 3. Now, of course, the x and y components here are on the unit circle. And so we can simply say x is going to be cosine of theta, y is going to be sine of theta, and z is going to be the square root of 3. Okay, and so that is our parameterization r, cosine theta, sine theta, radical 3. And of course, we have our function f up above there, which is xz, yz, and xy. And our function f becomes, when you plug in your parameterization here, we're going to have x times z, so that's going to be radical 3 cosine of theta, y times z, which is radical 3 sine of theta, and x times y, which is sine of theta cosine of theta. Okay, so here's f. Now let's compute dr. dr is simply the derivative of all of these with respect to theta. So that's negative sine of theta, cosine of theta, and 0. And then we just need to do f dot product with dr. And so we're going to take the dot product of these here. So we're going to have negative radical 3 sine theta cosine theta plus radical 3 sine theta cosine theta plus 0. And notice this is equal to 0. And so our integral is the integral of 0, right? d theta from 0 to 2 pi, but it doesn't really matter because that's just going to be 0. Now you could also go back and do this integral along the surface by using the other formula, but you'll see that it's a little bit more work. You'll still get 0, but it'll be a little bit more work. So if you want to try that on your own, be my guest. And that concludes this video lesson.